And today, Rebecca R.G. will talk about classifying neural ideas.
Thanks to all of you for coming. So I know a bunch of you were at my Wicca talk. I swear I'm covering different stuff today, but the background is overlapping. So just let me keep touching base with you on like, oh yeah, we can go through this quickly versus no, I should see that again. So just to remind you of the setup. So this is work on neural ideals, which were created because of the way that certain cells in the hippocampus fire in the brain. So what experimental neuroscientists will do, not me, is they've got a rat running around a pen, and the rat's kind of going everywhere. And while it's running around, they're recording ballpark of 100 neurons. And from the data from the rats, they know when each neuron fired, and they know where the rat was at each point in time. And from that, they can make a kind of diagram. So over here, U1 is going to be where neuron 1 is firing. U2 will be where neuron 2 is firing, and U3 will be where neuron 3 is firing. Normally they'd be doing 100. I'm not going to draw that. And so the information that we take is the neural code, and what that's recording is which neurons fire together. In fact, in an experiment, they might not even draw this diagram. They might just record which neurons fire together, but you can make this picture. So here we have places where no neurons fire. Just 1 and 2, 1 and 3, or just 3. And that's it. No other combination fires together, if I wrote this down right. Yes. And we can turn that into binary strings. So we record a 1 if that neuron's firing, a 0 if it's not. So we'd get these. So notice in the string, the length of the string is equal to the number of neurons. It's binary. So this is just a subset of all the possible binary strings on three symbols. So this is still not super algebraic. It is a code for people who do coding theory. This is a terrible code. It's not a linear code. It doesn't have to be closed under anything in particular. It's just a list. But what Curto, Itzkov et al. So around 2013 is when this paper came out. What they did is turn this data into something more algebraic. And that's what I'm going to focus on today. So the first sort of like thought on how you would do this is a very algebraic geometry thought. It's, I can look at the polynomials that vanish on these. So if we start in this field, where it would be same number of variables as neurons, if we start here, we can say what's going to vanish on every single polynomial here. So one thing that'll vanish would be there's it'll be 1 minus x1, x2, 1 minus x3. And this will vanish any place that x1 is 1, either x2 is 0 or x3 is 1. Let me give everyone a second to stare at this and confirm that they believe that this works. No. But this is the most straightforward algorithmic way for me to write one down without having to think about it. We'll get to that. So looking at this, though, this one is sort of like I built this from this code. It's somewhat particular to this code, although not very like least degree. But here's another one that's going to vanish. But this doesn't tell us anything because this one's going to vanish literally no matter what I write down. This will always vanish. So this is a Boolean relation. And the Boolean relations, they were thinking, well, we'll look at the vanishing ideal, but it turns out we don't care about this part. So the idea of the neural ideal is that it's polynomials that vanish on every code word except Boolean ones. And that sounds like it's kind of ill-defined because you usually can't be like except these in defining an ideal. But it turns out that you can, in this case, it required proof. But what they ended up figuring out is that what you get when you do this kind of thing can be defined a different way. So what they looked at instead, so this is going to be the definition of the neural ideal. That was sort of the idea of it. Here's an actual definition. So look at all relations that are of this form. So any relation that says some intersection of UIs is contained in some union of UJs. I'm going to finish the definition and then we'll immediately go back to the example. For each of these, take a generator, and we're going to take a product of xi's times a product of 1 minus xj's. So over here, some relations we have are U2 is contained in U1. U2 intersect U3 is empty. And U1 intersect U2 intersect U3 is empty. So for each of these, I do have a different color. For this one, we write down x2 times 1 minus x1. Apropos of, no, we don't need that. We could write down x2, x3, and x1, x2, x3. And if you're looking at this and you're thinking, I want these to be generators for an ideal, what do I not need? The last one. Yeah, I really don't need this. And sure enough, that's not required.
Do you need your segmentality to be disjoint?
Oh, yes, I should have said. Thank you.
The Boolean are still there.
Yeah, this is explicitly to rule out the Boolean relations. Thanks. Yeah.
So there could be things that are not in your code. Like a particular like what isn't 111?
So for this ideal, it would, this one wouldn't be 0 on 111, so I don't think so. So it should correspond, yeah, with the caveat, which I'm about to show you the fix, but caveat is, right, this isn't like a particularly well-defined set of generators. If you have a set of generators, you can come up with the original neural code. You're not going to end up accidentally getting a different one, but if you've got two neural ideals, like how do you know if they're the same? Because the set of generators isn't particularly unique. You'd have to do some work. Only you don't. Because the other thing they did is come up with a canonical form. So here, it's going to be like this, but add the word minimal in some very strategic places. So for all relations, intersection UI is contained in union UJ, such that no UI or UJ can be removed. Then we'll take this product again as our generator, where I didn't write the sigmas and taus, but those are the sets again. So looking at this one, over here, this relation, I could remove something because I didn't really need to write down U1. If I took out U1, this relation would still be true. So this is like not needed for the canonical form. So looking at this, you might think in some sense, this is like a minimal generating set, and you know, we should be so lucky, but it's not. So if we removed U2, we'd be saying empty set is contained in, no, we'd be saying the empty intersection. And we're saying the empty intersection is the whole space, so that wouldn't be true. Yeah. But let me give you an example that's equally sort of like the simplest one I can usually come up with is if we had U1 equals empty set and U2 is contained in U1, something like that. This would be an example of, yes, I could absolutely remove this U1 and replace it with the empty set. So in an example like this, yeah, you would just write. And sure enough, the canonical form is this. So from these, it looks like you're decreasing the number of generators, but I think that's actually very much not the norm. In some sense, removing generators is like degenerate cases. And lots of examples that like a person would write down are going to be that kind of degenerate case. But I don't think that's the general case. The general case is very much more to get the canonical form, you have to add generators. And the example, I mean, I did do this in Wicca, but let's do it again because it's the shortest one to write down here. And that's if I have U1 is contained in U2 and U2 is contained in U3. I say I know these are relations. I'm going to get x1 times 1 minus x2 and x2 times 1 minus x3. But if these are relations, then I also have to have this relation. Like it's also true. Maybe I didn't think of it in the first place because it seemed kind of obvious, but it is also true. It is also minimal. And so this is actually the canonical form. It requires all three things. So something about this that's kind of neat though, is the results that I talked about at Wicca, I'm not going to spend much time on now, but it's something of how do you come up with this third generator if you weren't looking at the receptive field structure? And how Hugh Geller and I think about doing this is if you look at these two first two generators, we have these two things, an x2 in one of them and a 1 minus x2 in the other. And we know from that you take the LCM of everything that's left and that it also better be a generator. And we come up with this. Not going to focus on that paper today just because I've already done it recently. But there is sort of a visual way, if you've got some of the generators, to come up with the other ones.
Can you say it again? So you're saying if I took the x2, I take everything with an x2?
We take, if we have something with an x2 and something with a 1 minus x2, we take the LCM of the rest of those generators. Yeah, it's slightly more subtle than that, but not much. But if you're looking at this, you're like, this is kind of terrible from a commutative algebra perspective. Nothing's local, nothing's graded. Maybe we have to redo commutative algebra to work with these. They're called pseudomonomials. And in fact, in the original Kurto-Itzkov et al. Paper, that is what they did. They came up with a theory of primary decomposition for pseudomonomial ideals. And it does work. A lot of stuff does work. But it would be nicer if we just didn't need to do that. So the next paper I'm going to talk about is Sema Gunturkan, Jack Jeffries, and Jeffrey's son. And I think this was literally an REU. Sema and Jack had Jeffrey as an REU student and did this paper, and it's fantastic. So the motivation is, how do we make these be local graded, whatever? They chose graded. So for this, we're going to let R. This is our initial ring that we've been working in so far. We've got a variable for each neuron, and we're over the field with 2 elements. And then we're going to look at this extension ring. So now we've tacked on a new variable for every neuron. So instead of having 1 variable, each neuron has 2, and that makes the math certainly a little bit interesting. But what they do is something really like simplistic looking. If you've seen polarization of monomial ideals to make square-free monomial ideals, this is the same vibe. So we have a map P that inputs a pseudomonomial, Oh gosh, I've lost track of this. Yes, spelling is good. Inputs a pseudomonomial and outputs a square-free monomial. So this is an R and this is an S. This isn't any kind of homomorphism ring map, whatever. It's just a map that takes pseudomonomials to square-free monomials. So what it does is if we have some product of xi's and 1 minus xi's, it gets sent to the product of the xi's and the product of the yj's. Whoops, that should be a j. And this map is, fairly terrible. One way in which it's terrible is that if you want to look at what it does to an ideal, it gets a little subtle. So for I an ideal, so P of I, we're going to define, and this is what we have to do to make things work out. This is going to be generated by P of F for all F in I. We can't just take a generating set and polarize those. It won't work. Let me show you an example of why that won't work. So remember my really simple kind of annoying example over here? So if I'd written down this non-canonical form, I had x1, and then I had x2 times 1 minus x1. And if I look at that ideal, that contains x1, or sorry, x2. If I just tried to polarize these generators, I would get x1 and x2y1, which doesn't contain x2. So if I just try to polarize generators of an ideal, most of the time that's going to fail. It's not going to get the right corresponding thing. However, their main result, or one of their main results, is that if you do this to something in canonical form, it does work. So if I is the canonical form of a code C, then, and say I has generators like G1 through GK, then P of I is actually going to be generated by just polarizing the generators. So if you're in canonical form, we can just polarize the generators. Everything corresponds nicely. And why that's valuable is that we can now make the following definition, which is the polarized canonical form of a neural code C is going to be like P of CF of C, but I'm just defining it this way using this theorem. We could have made the definition before. I made it now because now we know that it's something that's not too bad to write down if you have the depolarized canonical form. So the obvious question is, sure, we can do this terrible polarization map, but like, what does that get me? Is it good enough to retain any properties? And the answer, fortunately, is actually yes. So the key idea is that we have a map from S to R that takes xi maps to xi, the 1 and 0 map to themselves, and then yi maps to 1 minus xi. And the point of this is that this is essentially the quotient map from S to S mod xi plus yi minus 1. And this thing we're quotienting out by is generated by a regular sequence. So because they form a regular sequence, we just get everything nice that we want. So properties in general, like most nice properties are going to pass. The thing I'm going to really care about today is that if you take a minimal free resolution of a polarized canonical form, so C is a neural code, take the canonical form and polarize. Oh, right, this map is called D. If we look at D of the resolution is a resolution, we no longer know what minimal means because we're no longer in this graded setting. But if we take a minimal free resolution of the polarized thing, we can compute, projective dimension, Betti numbers, regularity, whatever we want. And then we depolarize. And essentially what we do when we depolarize is, right, if we had before like 0 to S to the BT to like S to the B1 to S to the B0, if that was our resolution, and we have some maps here, essentially all we're doing is now copies of R, same number of copies of R. Oops. And in every single map, like the matrix of the map, we're just replacing the yi's with 1 minus xi's. That's all that's changing. So the result here is that this is called the canonical resolution. And that's essentially what I'm going to be studying. So this is a good time to pause for questions on anything so far. You're actually getting a resolution. Because we were killing a regular sequence, stuff gets nice. Yeah.
Say again, your quotient map, so I see how to find.
Yeah, so D is the map, this map. It's essentially equivalent to the quotient map. You could view this as factoring through the quotient, and then this is isomorphic to R. Yeah, I guess I did not say it explicitly, so I'm glad you asked. Yeah. Other questions or anything you want more detail on for now?
It's just the saturation. I don't mean it's corresponding here. We just saturate with respect to the ideal. We can't have two. Can't have both X, Y, and Y.
Yeah. Yeah, that is kind of the idea. The original algorithm for computing the canonical form was basically take a primary decomposition, and then remove things that are divisible by an xi and a 1 minus xi. Get rid of stuff that's divisible by anything else. Like you take the primary decomposition, any generator that has like an xi and a 1 minus xi is going to go away, or any, not generator, ideal. So actually the proof that Hugh and I did was basically going through that primary decomposition and seeing what actually happens. Yeah. But so all of this is like set up, but really the goal of this research is to be able to talk to neuroscientists and say, if you give me a neural code, I can give you some sense of like what other neural codes it's like. Or like I can distinguish between these two. They have some feature not in common. So all of this setup, what it lets us do is start getting results on how to classify neural codes. So the particular class of neural codes that I've been working with so far seem like a good starting case, are called inductively pierced codes. So this definition is from Curry, Jeffs, Youngs, and Zhao. There's a formal definition. I find it's a little bit hard to understand, so I'm going to define it by picture for you. Happy to go through the actual definition at the end if anyone wants. Yeah, I did this for you. Yeah, it's much better. So here's what an inductively pierced code looks like.
they called?
Inductively pierced. Yeah. So this one is good to look up for because it's by picture. So here's a zero piercing. And if I'm going to track my number of zero piercings, okay, so I've got one zero piercing. I'm going to draw one piercing. It intersected the other one in such a way that any possible sub-intersection exists. There's places where none of them fire, there's places where each of them fire, and there's a place where they both fire. So that's a one piercing. Here's another one piercing. So again, it's sort of like the most general it could be. Here's a two piercing. Right, every possible sub-intersection exists. If this one intersects these two, there also has to be a place where all three intersect. There also has to be a place where the other two intersect without it. They all have to fire separately, and there has to be space where none fires.
Why does that increase the number of piercings?
Because this is a if we had these two already, this is a two piercing of those. Yeah,
So each time you add it.
So you're doing
Yes.
some sort of shelling like thing also, so it could depend on which way you have.
yes. And I'll get to that in a second. So let me add the kind of one piercing that'll be the least intuitive. So here's another one piercing.
Are the codes always coming from a two-dimensional?
No. If they're filming a rat, yes. If they're filming a bat, no. If it's coming from, say, the nose, then no, not at all. So part of why this is worthwhile is it's hard to draw them. So if we can get like algebraic invariance, it'll be good for studying like the olfactory senses where like, this is probably many dimensions. Yeah, but I'm gonna keep drawing you 2D pictures. So this over here, it counts as a one piercing. It's a one piercing that takes place inside of another field. But inside of this field, we have a place where neither of these two fire. We have just this one, we have just this one, and we have both. And this is allowed. So part of the definition of inductively pierced is that there should be a piercing order, namely an order in which I can draw these such that each time I add a neuron, it is a piercing. So the order I drew these is this. And that's a valid piercing order. But that's not the only valid piercing order. It's not necessarily unique in general. Really, the order in which I draw 1, 2, and 3 doesn't matter at all. I could have done 3 or 2, 1, 3, or 5. That would be fine. But it's actually even more than that you can do. So here, 4 was the 2 piercing, but I could have drawn 4 first, and then 3 would have been the 2 piercing. And that's okay. So I could have done 1, 2, 4, 3, 5. The only thing here that really matters in this example as far as order goes is that the 5 has to be drawn after the 1.
Just had 1 and 5 by itself and nothing else. What would that mean?
Oh, sorry. If I just had 1 and 5 like this, then 5 is a 0 piercing of 1. Yeah, both of them are 0 piercings. 5 happens to take place inside of 1, but still is a 0 piercing. But we would not be allowed to draw 5 first. So piercing orders are not unique, but there can be a bunch of them. But something that it would be nice to know is like, is the number of each type of piercings a feature of the code, or can it change depending on how you draw it? So good thing for us, it can't. So this is a theorem of myself, Hugh Geller, and Nora Young's. So I'm going to say some things about like homological invariance and also in a bit, but no matter what piercing order you choose, the number, say, j sub I of eye piercings is fixed. So once you have a code, the number of each type of piercings will be the same no matter what order you choose. It's just, whether 3 or 4 was the 2 piercing could change.
So didn't you say 1, 2, and 3 doesn't matter in which order you go them? But this used to matter. You can't draw 1, 3, and then 2, right?
Ah, you're right. Yes, we can't draw 2 after 1 and 3. Thank you for pointing that out. Yeah. So let's take a second and go back to the Curry, Jeff Young's and Zhao paper and look at what does this neural ideal look like. So it turns out these are very, very nice. So the neural ideal for these is quadratic. And for all I not equal to j, there exists at most one generator from the set xi, xj, xi, yj, and xj, yi. That's a set. So this is a result from their paper. And what this comes out of is what we're saying is for any pair, either they don't intersect or one's contained in the other, or they do intersect and we just don't care. Like that doesn't show up. Yeah. Yes. Yeah. Very much does not hold outside of there.
There's 3.
3. We can't have yi, yj because that would tell us that some unions span the whole space, and we've explicitly disallowed that. Yeah. So for this one, the neural ideal is going to have, so 1 and 3 don't intersect. So we'll get x1, x3. 1 and 4 don't intersect. So we'll get x1, x4. 5 is contained in 1, so we'll get x5, y1. 2 intersects everything. Don't need to write anything new down there. 3 does not intersect 5. And 4 does not intersect 5. So this is the generators for the canonical form. And they are exactly as we said. For any pair, we have at most one generator, and it's either going to be 2 x's or an x and y.
Sorry, are you saying like 2 completely disappears from the picture somehow?
2 intersects every single other thing, but it's not contained in anything. So yeah, there's no generator that involves it. 2 is just like, I interact with everything. Yeah. So something that I'm not going to focus on much today, but that is interesting about this. Let me draw one quick side note picture over here, which is there's a kind of graph that people draw here, but it's not necessarily the one you'd expect. So we just number these by the neurons. We don't distinguish between xi and yi at all. And we draw a line segment between any 2 where that pair is not in the canonical form. So we draw 1, 2, not 1, 3, 1, 4, or 1, 5. 2 has to connect to everything. And then 3 and 4 should connect. Let me give you a second to make sure you believe that what I just did.
Can you say it again?
Yeah. So we put a point for every neuron or vertex, and then we connect 2 vertices if there's no generator for that pair in the canonical form. So this is weird for 2 reasons. One is that it's sort of the opposite of what you would expect if you're drawing an edge ideal. And the other reason is that we don't distinguish between xi and yi. Yeah, did you?
Different than j exists like that, sorry.
Oh, for each I not equal to j, there exists at most one generator from this set.
And the question, sorry, was before me, but like, so like, if I choose the piercing orders, I have that. But if I choose something that is not allowed, will I have a different like inductive piercing code, or it is not at all?
So this code is inductively pierced because there exists a piercing order. Yeah, so not every single order I could write down the neurons is a piercing order, but as long as one exists, it's inductively pierced.
And which it's not super clear for me which one. Inductive piercing.
So it needs to be the case that each time we draw in a neuron, it creates a piercing. And I haven't really given you the formal definition of that, which is probably why it's fuzzy. I can get you the formal definition at the end. I find it takes 10 or 20 minutes to understand. It's mostly why I didn't. But for example, once we draw on 1, 2 is a valid 1 piercing of 1. So in each step, we drew something that was a valid piercing, so it counted as a piercing order.
It would be a problem drawing 2 after 1 and 3
Because 2 would not be, if we drew 1 and then 3, and then afterwards we tried to draw 2, 2 should be a 2 piercing because it's intersecting 2 things. Yeah, but they don't intersect, so it's not valid. Yeah.
Do we get the same generating set from each piercing order?
Yeah. I mean, as long as we label the neurons like this, the piercing order isn't what determines the generators. Yeah. If I swapped some of the names of the neurons around, I would get something different here, just, symmetric group action. Yeah. But I mentioned this graph because it is something that people are looking at, but it is quite different from how we look at edge ideals and such. So, but a particular feature of inductively pierced codes is that this graph will be co-chordal, which means if you instead draw all the line segments for the things that are in the neural code, it would be a chordal graph, which does make me wonder why they didn't draw the other one, but yeah, it is an if and only if. Yeah.
Would that be true though, because you're ignoring the fact that Y1, like the edge ideal of that, that's another variable, or another vertex. I mean, maybe, it seems strange to me because like the thing on the right would be correspond to a graph of 6 vertices, and the thing on the left only has 5 vertices, so.
So the vertices are for the neurons, so we'd get.
Well, I guess the 2 didn't show up here, that's part of what's going on here, right? Because you have Y1 showing up.
Yeah.
It's Y1 acting.
Oh, this vertex represents both X1 and Y1. This graph doesn't distinguish between this 5 being inside of 1 or just being a 1 piercing of 2 that's outside of 1. The graph doesn't distinguish. Yeah.
Maybe this is wrong, but if I take the non-edges of this graph
Mhm.
and I write an ideal like X1, X3, for example, and then I take the intersection of those ideals, do I get this thing, but with YI being XI?
I think so, yes.
And what's the theorem? This is co-chordal,
This is co-chordal.
meaning, and that the theorem is that if it's a inductively pierced.
You're inductively pierced if and only if this graph is co-chordal. But you can read the piercing order from this graph. So you read it sort of in reverse. So I know that 1, 2, 3, 4, 5 is a piercing order. So 5 would be the first thing to pick off. This is going to require some colors. So I can pick off 5 because everything it's connected to forms a clique. Let me start a new board and just do this out. The complement is chordal. Yeah. Okay, so I have 1, 2, 3, 4, 5. And I've got 1 connected to 2, 2 connected to everything, and 4 connected. Thanks. So if I have a valid piercing order, what I should be able to do is go, okay. 5, everything it's connected to, just 2 forms a clique, so I can remove 5. And then I'll get if I look at 4 now, everything it's connected to forms a clique again, so you can remove 4. So now I'm left with and then 3, everything it's connected to forms a clique again. It's not an interesting one, but it is. And I can remove that, and I'm left with 1 and 2. And now 2, everything it's connected to forms a clique, so I can remove 2 and then finally 1. And that's a way to tell if you have a correct piercing order. It might be the most common way to tell if you have a correct piercing order.
Person?
Yeah, yeah. So the piercing order is 1, 2, 3, 4, 5. So we remove 5, 4, 3, 2, 1. Yeah. Okay. So I do want to talk about our results on Betty numbers, but questions on this first? Yeah.
Follow the is, so in that case, you know, x1 minus y1 is a non-zero divisor on the ideal generated by those pairs, and so that, from that perspective, it feels really natural that we don't really care about who's x1, who's y1 when we draw the graph. Is it always the case that xi minus yi is a non-zero divisor on the ideal?
Yes, because yi is essentially taking the role of 1 minus xi. So you would hope.
In general, how much do we know? So then we have replacing xi with yi. Now we have, you know, the degree 2 part of the Stanley-Reisner ideal of that. How much do we, sort of in general, do we expect to know about Stanley-Reisner ideal if we're looking at its degree 2 part?
No idea.
Actually, you're replacing, xi with y.
Especially why.
No, not even.
But
that.
it's really
One
yi
minus-
is 1 minus
Yeah,
xi.
change it. The regular element is not xi plus y, it's a xi plus y element. So it's sort of like you're modding out, you're
So
replacing xi.
xi plus yi should be equal to 1 when we do the quotient. So I think we could do differently what you were saying and get different information, and I just don't know what it would tell us. But to keep the neural structure, yi is really xi minus 1. Yeah.
So there's this result about, there's exactly one generator for each of these sets. Is there anything about like, can I, like which inductively pierced neural ideals can exist? Like, is there one where if I would just replace the yi with an xi, does that exist?
Yeah. And that would just be if I took this 5 and put it up here instead.
Okay, so all of them.
Yeah.
exist.
If you do what, if you change all the x's to y's?
No, if you change this y to an x1, which would be like moving this 5 over here. Yeah, you can do that. Okay, go back.
Not a random.
Polarization is not, but depolarization is.
Have some ring over f2 and some variables,
Mhm.
an ideal generated by those degree 2 things. And there it is the case that xi minus yi is on the xi. Then you can look at the ideal in the graph.
Mhm. So
Why is this so wrong perspective? Why did I then?
Oh.
Okay.
it's only the wrong perspective. Like it might be a useful perspective. It's one I think people haven't looked at. Because of the association with the yi with the 1 minus xi, because that's what we do when we depolarize. I just don't think anyone's looked at what you've said.
Actually, I don't know if it is. So if I have x2 times y3 and x2 times x3, which I shouldn't have.
No, because then we'd actually have
But
just
if I
x2.
did, Then an x3 minus y3 is not a non-zero.
But if we had this, the canonical form would contain x2 and not these. So
So you're saying that for these particular ideals, xi minus yi might be.
yeah, I think for inductively pierced, it seems possible. Yeah. Okay. So let me get to our results. And this is myself with Hugh Geller and Nora Youngs. So let C be a neural code. such that no union of UI is equal to the whole space. So I'm always assuming there's a space where nothing's firing. And 2, no UI is equal to UJ for I not equal to J. If you had a neural code where either of these were true, you could just expand X a little bit or just remove one of these to fix this. So under these circumstances, the polarized canonical form of C is inductively pierced if and only if, C is inductively pierced if and only if the polarized canonical form is quadratic and regularity 2. So I think we figured out pretty quickly that inductively pierced codes had regularity 2, but what's nice is really if you're a polarized canonical form at all and you in quadratic and regularity 2, you have to be inductively pierced.
Sorry, what the conditions are for, this is a neural code such that the union.
Actually.
The union of,
No union of U sub i's is the whole space.
what's the second?
No,
No,
yeah,
so no two are equal.
no 2 are equal. If you had a neural code where they were equal, you could just ditch one of them.
Union of, like the union of everything is X, right?
No, it's not, no union of them is all of X. There has to be a spot where nothing's firing. I'm essentially saying we have the all zeros code word.
Union of everything is not X.
Ye-
Maybe that's an easier way to
Oh,
say it.
yeah.
Yeah.
How about let's do that?
Everything.
Yeah,
When I think of quadratic regression, I mean, it's a linear resolution, and I think, isn't that, like, at least for the edge angles of the graphs, that is a characterization, right? Isn't that Froberg's theorem?
yeah, we're using some results of Froberg's to prove this. Yeah, it's very related.
It's the great.
Yeah, it has to be the canonical form of some neural code for our result to even apply. Yeah, but yes, we are relying on Froberg's results to prove this.
So the statement is P of that, or you mean just the ideal in the X's and Y's?
Yeah, I mean the ideal in the X's and Y's.
And what is the program result? In this case, I forget.
That was the edge ideal.
Oh,
So we're short on time, so I'm not going to give you the combinatorial formulas for this next result, but I have them if anyone wants to see. So suppose C is an inductively pierced code. And J is the polarized canonical form. So there exists a one-to-one correspondence between the graded Betty numbers beta ij of S mod J and the list of how many piercings there are of each type. So that was J sub I is the number of I piercings. So if I know how many 0 piercings, 1 piercings, 2 piercings there are, I can output the Betty numbers with a not too bad formula, and vice versa. If I have the Betty numbers, I can output the J's.
You need all the betting.
Yeah. Yeah. These are all finite, right? We're working over a polynomial ring. Everything's finite projective dimension, so it's not too bad.
So if you have the graded Betty numbers, those are giving you the sizes of piercings, is that what you're saying?
How many piercings of each type there are? So like this list 1, 3, 1. Yeah.
So what is the beta ij number then? You're
Graded.
saying that you're not saying.
No, I could write it down if you want. So actually it doesn't need to be the graded Betty numbers. It could just be the regular Betty numbers. That's fine too. But you'll notice the thing this doesn't capture is whether that 5 is inside or outside, that kind of thing. So actually, we also have a result that if you define a multigrading, where the x's are degree 1, 0, and the y's are degree 0, 1, you can output numbers of piercings and what they're inside. So that's our newest result. So I definitely don't want to put it on the board, but we're pretty sure we're right. So basically, if you have an inductively pierced code, we just from the canonical form, we can output the Betti numbers just in Macaulay 2, and then we can come up with how many piercings of each type there are, which tells you a lot about the geometry, which is good because in some sense, when you have 100 neurons, drawing the picture is the hard part. So we can tell you quite a lot about the picture. There's another result that maybe your code's not inductively pierced, but you have some neural code and you know the Betti numbers of the polarized canonical form. If you add a piercing to it, we can tell you how the Betti numbers change as well. You look like you had a question.
Just like there is a junction between the Betti numbers and this JN is the number of the
N piercings.
So like in the picture,
Yeah.
it would be
J0, J1, J2. Yeah, and I think I'll stop there. If people want to see the combinatorial formulas, I have them right over here, but they're not that exciting.
So do they actually have examples of codes that you're interested in that like are in the 100 neurons or higher?
So it's like you can get a neuroscientist give you a data set. I don't currently have things set up to process it. This is part of why I'm working on my Macaulay 2 package. And there's already Sage code as well. So ideally, I'd like to get a grad student to go do a lot of that. And go process some data sets and compute stuff. The issue is there's no particular reason to assume a data set will be inductively pierced, so we need more results. But there's some sense in which we want the neural ideal to be independent of slight wiggling. Because when we say like this is the firing field, what we actually mean is we decided if you're firing above like this rate, that'll count as firing and that'll not. So something that's kind of in general position seems like a good choice. Whereas like if you had something like that is not invariant under any wiggling because the boundaries line up a bit, versus something like this where a little bit of wiggling and it would still kind of be the same.
Could you do sort of like a EA sort of thing where you have fuzziness in the sizes even?
So yes, people are doing TDA on this stuff. We don't have yet the right idea for the ring that'll capture that. So that's something people are working on. Yeah.
So for this last theorem that you I think have the result of the previous one, right? So these are the quadratic vectors. And I think in this specific case, I think it's true here you have inner quotients. Generally speaking, I think it was another ideal regularity bigger than 2 but regularity.
Yeah.
Yeah, I think
Which gives you a way to put state numbers. So I'm wondering if the formulas they are related.
I probably, and I think the thing that's distinct about these is our formulas for the Betti numbers are in terms of these J's. And I feel like in most other contexts, these aren't what would naturally come up. And that's probably the main difference. Yeah. Yeah.
Then it might actually tie up.
Yeah, it might.
Then I also have another question. I was wondering if it was one dimension bigger version where you the initial thing at the top.
Yeah. So inductively pierced codes don't have to be in dimension 2. As soon as you have a 3 piercing, you have to go up to the next dimension. So the higher piercings require higher dimensions, which is why I only drew up to a 2 piercing. But yeah, inductively pierced codes are not a 2-dimensional thing.
Then
Yes. Because in some sense, so the thing that would create higher degree stuff is something like this would force a generator of higher degree. Because any 2 intersect, but all 3 don't. But inductively pierced codes can't have this. So that's, yeah, this is not the only thing that forces a higher degree generator, but it's an example, and we can't have that.
So examples and so just the dimension of this ideal in whatever, I mean, so is it more the code dimension or whatever, it's I mean, what kinds, is it really high dimensional for the neural data or is it?
So neural data is apparently typically a little bit like a lot of neurons will have very similar firing fields. There seems to be a lot of duplication and there's more firing fields near like a particular reward or something and fewer in sort of like empty space. So I'm not sure how to describe what would typically happen.
Actually, maybe my question doesn't really make sense because dimensions, because you have, oh, maybe everything's going to be dimension n essentially. I mean, because you're going to have xi, for each variable, you're going to have either xi or y, I, and it thing. Smaller.
So if you're a zero pierced, then you always have one of these three generators for every pair ij, but this doesn't have a one for every. So like x2 didn't appear in here at all, and it doesn't have to. So I think it could vary a lot. Yeah.
I think should the dimension be related to the dimension of this ideal, right? And that would be the dimension maximum and that side of your graph. Right. So I don't have a good intuition of what these graphs look like.
I don't know.
You mean the graphs,
Well, I guess like
are that where this is.
Oh, the graph moved up.
over here, these ideal P, right?
Mhm.
They're basically edge ideal. Yeah. right?
Well, sort of.
Sort of.
Like you could make it an edge ideal if you double the number of vertices.
Dimension. Dimension.
But I wonder if it would be possible to read something off of this graph, and I'm not totally sure just because we're sort of merging the xi and yi and the algebra doesn't understand that they're merged. Yeah.
So, yeah, like you're saying, you're merging all these things with this one graph, this whole family, and ideals that correspond to that graph. Are the Betty numbers related for that whole family, or are they all like,
Sorry, say again?
so you have the same graph for a whole family of ideals?
Mhm.
Is there a relation between the Betty numbers of that family, or are they just?
Yes, but not the multigraded ones. Because swapping out xi's for yi's doesn't, yeah, it doesn't matter so much until you get to the multigraded.
Graph for forgetting about the y's, just.
Mhm.
But if you have that map in that factors to that quotient, you always have one linear relation combining xi and yi, so you kind of see the algebraic there. That
Yeah.
each one of those cuts down the function by that, which would be the same as.
Yeah, just instead of yi being x, it's like 1 minus xi, but yeah. Yeah.
This doesn't dimension.
No, that's true.
So last question, just to repeat something, like to get from the thing to the graph, you're taking each edge for each proper intersection, basically.
Yes.
Okay.
Yeah.
And you said that this concorda is a if and only if is fit.
Yeah.
Okay. And what happened now? Sorry.
Over here?
Yes.
This was me demonstrating how you can read off a piercing order from the graph. So you do it in reverse. So if 1, 2, 3, 4, 5 is a piercing order, you can remove them in the other order, and you can remove one if everything it's connected to forms a clique. So 2 is a clique. This one's more interesting. We want to remove 4 next. 2 and 3 are a clique, so we can remove 4.
Wait, so can you remove one first?
We
Because
could have removed
two
one.
Is by itself, you're saying everything it's connected to has to be.
Yeah. Everything that it's directly connected to. So the problem is, depending on what we remove, we might run into some issues.
You maybe show like you said, like I cannot put 5 before 1. Like what will be here in this?
Yeah. So I can't do 5 before 1 based on like
Yes.
the rules of how we're adding generators. And the question is, why can't we remove it from the graph?
How-
Maybe I drew the graph wrong. Let's see. 1, 2.
Is it an if and only
Well,
if?
1 and 5 are the same.
Yeah, because it does look like you could remove 1. So it's possible that this isn't the perfect way to come up with a piercing order. It might not be an if and only if, but if it is a piercing order, then you can do this, might be the case. Yeah, that was kind of an aside. I haven't worked with this so much, so yeah, worth looking up.
Okay, if there are no more questions, let's thank Rebecca again.